Now we're going to see the introduction to the harmonics and fundamental frequency. Harmonics and fundamental frequency. So, in the previous video, we saw what happens when we have a string attached to an end and we produce a sinusoidal wave continuously. Now we will see what happens if this string is attached to two ends and we string the string. So we will see a pattern of sinusoidal movement. Now here, if we do the experiment, we will see that the resultant wave could also be a standing wave, but this standing wave can have many shapes. One is something like this. So it doesn't matter how much we are moving it will always have this shape. This is it, and then it is coming reflected. So it's one or the other. We will see first this and then this, but very quickly we will see this. And so if it is attached to both ends, but if we produce this, we will see this, and this is a, for example, a musical instrument. This is the length, and remember that the propagation, the velocity is equal to the frequency times the wavelength. So I also have frequency equals to the velocity divided by the wavelength. Here, remember that when any point is not moving at all, that's a node. So here and here I have a node. These two are nodes. Remember the equation of the standing wave is something like 2a sine of kx sine of omega t. Let me find these two ends. So that means this is y of x and t. That means that y of 0 t is equal to 0. That is true because when x is 0, I have that all this is equal to 0. And the other is y of lt is equal to 0. So when x takes the value of the length of the string, I have that all this will be 0. So I have that sine of kx is equal to 0, actually of sine of k lambda is equal, length, when x is the length of the string. I'm talking about the last point. So I have here that k, the length is equal to 0, p, 2p, 3p, etc. Actually, you can put this first as x, and sine of kx. So I have that x is again 0 over p, 2p, 3, 0, p, 2p, each one of these divided by k. So again, x is equal to, remember k is 2p divided by lambda. So I have 0 lambda over 2, 2 halves of lambda, 3 halves of lambda, etc. So again, the nodes are at a distance of half wavelength, and I have that the last one would be this one. Now, in order to this happen, I need that the length of the string be a multiple of the wavelength. So I have this one here. The length is equal to half of the wavelength, because here you have a node and another node. If we and the frequency here the frequency would be the velocity divided by, in this case, is here lambda, so lambda is in this case 2 times the length. So this frequency would be velocity divided by 2 times the length, and this frequency is called the fundamental frequency, and is the slowest frequency at which we can produce this. If we increase the frequency, it will not happen anything, and this will be destroyed and nothing will happen. But if we continue to increase the frequency, there will be another point in which now we will not see this, we would see something like well, I cannot draw it very nice, but here and here now I have 3 notes, 1, 2, 3 notes. The start, the end, and this middle note. So now, as you can see, the length of the string is now 2 half wavelengths. So now L is 2 halves of the wavelength. And this is because in order this to be true, we need, in order to have this pattern, sinusoidal pattern, we need that the length be a multiple of half of the wavelength. So let me call it n times half of the half wavelength. So the wavelength would be 2 times the length divided by n. So, for example, if I continue to increase the frequency, this again will be destroyed and nothing would happen. If I increase again the frequency even more, I would produce something like this. And so now I have that the length of the string is 3 halves of the wavelength. So I'm talking about n equals 3. So I have that the length is 3 half waves, 3 half length waves. And here we have now 4 nodes. In order to find the distance of the node, remember that each node is at half wavelength apart from each other. And now in the frequencies at which I'm coming to here, I have this that was the lowest frequency when n is equal to 1. When n is equal to 2, I have now frequency is, I have that the length is twice the half wavelength. So so here I have that this is 2 halves of the wavelength. So it's just n equals 2. So in this case, lambda is equal to the length of the string. So here I would just have that the frequency is the velocity divided by the length of the string. And if I increase even further and I return to see this, then the frequency is the velocity divided by, here I have that the length is 3 halves wavelengths. So the wavelength is 2 times the length divided by 3. So now I have the frequency is equal to velocity divided by 3 divided by 2, length divided by 3. So this is 3 velocity divided by 2 times the length. This is the frequency. So now let me do it with the general formula. If this is the wavelength, then I have that the frequency is velocity divided by 2, length divided by n, or the, let's say, the velocity divided by 2 times the length times n being equals to 1, 2, 3, 4, etc. the wavelength, the length of the string, that remains equal, but the n comes higher, and so if n comes higher, the frequency increases. So the lowest frequency, as we will produce this like envelope shape, this one is called the fundamental frequency. So this, that is f sub 1, is called the fundamental frequency. This is the fundamental frequency, and actually it is here just when n is equal to 1. And the other ones are called the overtones. So this f sub 2, which is f sub 2, f sub 2 would be when n is equal to 2 is p over, well, let me put it in general, it will be velocity over 2 times the length times 2, or in this case, I don't want you to remember the simplified version. This would be velocity divided by length. But the issue is that this is the first overtone. So I have fundamental frequency, first overtone, f sub 3 will be the second overtone, etc. So you can call it fundamental frequency and overtones, or you can say that this is the first harmonic, f sub 2 is the second harmonic, and f sub 3 is the third harmonic. So we have these notes, that is when there is no movement of this. Now in here we can also have these antinodes, and remember the antinodes are also at half wavelength apart each other, and from a node to the antinode is 1/4 of the wavelength. Now in the next video, in future video, we'll talk about resonance, and then we talk about standing waves on pipes or air, and we will talk about how this can be converted into musical instruments or produces the sounds on the music. Here I just wanted to clear that these movements that the particles are having, they are moving all at the same frequency, but they are not being displaced nor anything. So this is called the normal mode. And a string like this that can vibrate to different frequencies, the fundamental frequency and all the other harmonics frequencies, each frequency at which this string, each harmonic frequency at which this string can be vibrating has a normal mode. So we can have infinitely many normal modes. If we do not vibrate to this harmonic frequency, then we are not on normal mode. But enough for this video.